You are staring at a terminal on a heavily loaded server. A daemon has completely locked up, ignoring every input. Your immediate reflex is to type kill 9 and the process ID to force it to stop. The command works, the process is gone. But defaulting to this method bypasses the safety mechanisms that keep a multi-user system stable. The prompt returns, but the system is now in an undefined state. You might find that the process won't restart because a lock file was never deleted, or that a database connection is still hanging open, phantom artifacts of a process that vanished without warning. To understand why these artifacts persist, we have to look at how the Linux kernel handles processes. The kernel communicates with user space applications asynchronously through software interrupts known as signals. The word kill is a misnomer. The command does not natively terminate executing code. It simply delivers a specific numeric signal payload to a designated process ID. Treating kill as a weapon ignores this communication framework. Overriding the kernel's process management ignores how Linux constructs its environment, leading to system degradation. The strict resource management in Linux traces back to its origins. The kernel was built for highly constrained 1990s PC hardware, where memory was limited and every single byte had to be perfectly accounted for. Because of those constraints, a process in Linux is a complex data structure. After a program runs a call to exec, the kernel wraps it in a designated process context. This context holds the application's identity and environment. The kernel actively tracks credentials, user and group IDs, and key value arrays to verify exactly what system resources the process has the right to access. There is also the scheduling context. This is the precise information the kernel scheduler needs to safely suspend and restart the process while allocating CPU cycles. The process also maintains a file table, an array of pointers mapped via file descriptors. These tie the process directly to temporary files, network sockets, and lock files residing out in the file system hierarchy. A running process is a tightly bound web of allocated file structures. Abruptly severing the scheduling link leaves all of these resources dangling in an undefined state. This is why the kill command defaults to sending signal 15, or sigterm. Sigterm is a polite, asynchronous request from the kernel asking the process to terminate gracefully. Well-written user space applications and bash scripts anticipate this request. They handle it by utilizing a trap function. When the process receives that signal 15 pulse, the kernel pauses the program's standard execution. It then diverts the process to run that predefined cleanup routine. Inside the trap routine, the process manually iterates through its file table. It carefully closes open file descriptors and releases pending database locks. For the final step, the trap function explicitly deletes its own temporary .lock file. Only then does it cleanly exit back to the kernel. Utilizing sigterm allows the application to manage its own exit logistics, ensuring the integrity of the entire file system hierarchy. Sig9, or sigkill, offers no grace period. It is an absolute kernel-level mandate that cannot be caught, blocked, or ignored by the process. Sigkill completely bypasses the user space application. The trap function is ignored, and the application receives 0 processor time to react. Instead, the kernel takes direct action. It instantly deletes the process context and severs the scheduling link from memory. Because the user space cleanup function never ran, the file descriptors are severed violently. This is why the temporary lock files remain abandoned. The kernel removed the process before it could clean the disk. In a production environment, those stale lock files act as false positives. They prevent the daemon from successfully restarting, requiring a system administrator to step in and manually clear the dead files. Forcing the system into an inconsistent state violates the process lifecycle architecture. Sigkill is an administrative failure of last resort. The professional protocol follows a strict escalation path. Always send sigterm first, implement a timed wait to allow the trap to execute, and escalate to sigkill only if the process is completely unresponsive. There is only one edge case where sigkill fails, a process stuck in uninterruptible sleep, or state D. Waiting on hardware I/O, it will ignore even signal 9 until the hardware responds. Beyond termination, signals dictate active state management. Signal 1, or sci-hup, was traditionally used for terminal hangups, but it serves a specific function in modern software. Daemons like Nginx intercept sci-hup to trigger a zero downtime configuration reload. The internal config flushes and replaces its data, but the process context and active network sockets remain stable and unbroken. Applications also utilize user-defined signals, SIG USR1 and SIG USR2, to trigger custom internal scripts, initiate online upgrades, or reopen log files without halting execution. Navigating the signal architecture allows for predictable resource management. It is the difference between a system that recovers instantly and one that requires manual intervention to clear the wreckage of a forced exit.